Continuing on with bonding in polyatomic molecules, we're going to look at Sp2 hybridization. So our model molecule here is going to be BH3. So we have our boron, which has a 5+ nucleus, 5 electrons, 1s, 2s, and 3 2p orbitals. We have each hydrogen, which contributes an electron and a 1s orbital. So we have a total of 8 electrons, and we're going to have 8 orbitals. Okay, so that's plotted out on our little diagram here. We're in the XZ plane. The y-axis is coming out of the screen towards you, and there's also a PY coming out in that direction. Okay, so just like in the previous video, one of the things that we're going to notice is that the overlap between the 2py of the boron and the 1s of any given hydrogen atom is going to be 0. So because that overlap is going to be 0, there's going to be no net bonding that occurs with that 2py orbital. So that is going to lead us to call that, again, a non-bonding orbital. Non-bonding. Okay, and if we look at the 1s again, 1s of the boron is going to be much, much lower in energy than the 1s of any of the given hydrogens, and it'll be occupied with core electrons, and it won't be overlapping, so no bonding forming there. So that's once again going to be an occupied core orbital. Occupied core. Okay, so once again, like in the previous case, we want to generate a set of 3 orbitals that will be pointing in the correct direction towards bonding with each of the hydrogens, and the orbitals that will be orthogonal to one another. So we need to find the set of coefficients for the for the 2px, the 2pz, and the 2s of the boron that will give us the correct directionality towards bonding and also orthogonality towards the other bonding orbitals on the boron. So these are going to end up being 1 part S and 2 parts P, so they're going to be called, thus, Sp2 hybrid orbitals. So let's see what these orbitals end up being. So we can have psi Sp2 number 1 equals, and it's all about the coefficients that are in front, and I'm going to write them in a way such that we can more easily see what's going on. So I'm going to do 1 over the square root of 2 over 6 of 2s on the boron plus square root of 4 over 6 of the 2pz plus 0 for 2px. Okay, that's our first one. Our second one is going to be square root 2 over 6 2s. Then we're going to do minus square root 1 over 6 2pz plus square root 3 over 6 2px. And finally, our final orbital, our Sp2 number 3, is going to equal square root of 2/6 2s minus square root 1 over 6 2pz minus the square root of 3 over 6 2px. Okay, so let's analyze what these coefficients mean and why they have been chosen. Okay, so here are our orbitals here. There's Sp2 number 1 along the z-axis, as we can see. It's going to be, remember, the character of each of these orbitals is proportional to their coefficient squared. So this Sp1 is 2/6 or 1/3 s and 4/6 or 2/3 pz. So that's 2/3 p, 1/3 s, so twice as much p as there is s, and that's sp2. That's where the sp2 orbital name comes from. So that's mostly the pz orbital, 2/3 of it, and 1/3 s, so mostly pz, but a little bit more oriented towards our one axis than towards the other. Okay, and that's all along the z-axis because there's no contribution from the x, so we're just directly pointing this way toward hydrogen number 1. Okay, our second orbital, if we see here, is again 1/3 s. Then we have 1/6 of pz and 3/6 or 1/2 px. So there's 3 times as much px here as there is pz, and the pz is negative, so it's pointing in the negative z direction and then up in the px direction. And again, notice that the sum of these squares all add up to 1. 2/6 plus 1/6 plus 3/6 equals 1, 4/6 plus 2/6 equals 1, etc. So they are going to be normalized, but that we get our directionality there because the minus 1/6 and the plus 3/6 gives us that pointing towards that hydrogen number 2 up in the minus z and plus x quadrant up here. And similarly, we have our hydrogen number 3, which is in the minus z direction a little bit and a lot in the minus x. And you'll notice there it's the same thing, except for we switch the sign on the 2px part, now going down. So that's the nice part, that nice point that you see there, that all of these are normalized. The sum of the squares of their coefficients add up to 1, but also that they are orthogonal. So the orthogonality also implies that the overlap of any of these two orbitals is 0. So if we take, for example, 2/6 times 2/6 plus 4/6, so doing that whole overlap orbital in the way that we do for linear combinations, you'll notice that these overlaps all come out to be 0 as well. So we'd have square root of 2/6 times square root of 2/6 is 2/6 times square root of 4/6 minus square root of 1/6, so minus 4/6, and then 0 there. So you get 4/6 minus 4/6 equals 0. Same thing works out for the other combinations as well. So to state that in terms of an integral, as I have there, I can say the integral of sp2I over integral of sp2j is equal to delta ij. So it's Kronecker delta. It's 1 if I is equal to j, and it is 0 otherwise. All right, so then these overlap, these sp2 orbitals overlap with our 1s orbitals of the hydrogens, and they can form bonding and anti-bonding orbitals. So here are the cases where the overlap is positive. So we have bonding here, bonding there, buildup of density between the nuclei, buildup of density between the nuclei. And in the case where you have a negative linear combination, there's a node between the two nuclei, so there's a depletion of density between the nuclei, giving you an anti-bonding orbital. Same thing here between those two nuclei. Same thing there between those two nuclei, a depletion in our anti-bonding orbital. So writing that out, we have bonding in these 3 cases and anti-bonding over there. And to just mention again what I said over here, our orbitals being sp2 orbitals, and also as we can see from the coefficients of these are going to be 2/6 or 1/3 s, so they're about 33% s, and square root of 4/6 squared is 4/6 is 2/3, so about 67% p. And you'll notice that this also adds up the 1/6 plus 3/6, 1/6 plus 3/6 also adds up to 2/3 in each of those cases as well.